Welcome back to another video. Here we shall look at another very interesting problem based on the concept of permutations and combinations as applied to the counting of sets. This problem is taken from the book Principles and Techniques in Combinatorics, published by World Scientific Publishing. The authors are Chuan-Chong and Khee-Meng. It is from exercise 1 of chapter 1 on permutations and combinations. This problem will lead us to a beautiful proof for the formula for the sum of the first n squares. Then, as we venture deeper down the rabbit hole, we shall uncover two more elegant proofs for the same formula, one using an identity of the binomial coefficients and another using the principles of telescoping sums. This video should then serve as an ideal example of the various routes one can take to solve the same problem or establish the same fact. So strap yourselves for one interesting journey. Let us look at the statement of the first problem that will serve as a launch pad in enabling us to set up the proofs. Let S equal the set from 1 to n plus 1, where n is greater than or equal to 2. And let xyz in S cubed be a member of T if x is less than z and y is less than z. Show by counting the number of elements in T in two different ways that the sum from 1 to n of k squared equals the number of elements in T, which equals n plus 1 choose 2 plus 2 into n plus 1 choose 3. Now for the solution. Our approach will involve two methods for counting the number of elements in T, as suggested by the problem. We can start by picking an example to give ourselves a better understanding. Taking the example n equals 10, we see that the set S contains the elements from 1 to 11. If now z equals 6, x and y would both be free to take on any value between 1 and 5. This would account for 5 squared, which equals 25 elements in T. Similarly, if z equals k, an arbitrary value, then x and y would each take on any one of k minus 1 different values, resulting in a total of k minus 1 squared elements in T. With this in mind, finding the total number of elements just boils down to summing the expression k minus 1 squared over the range of valid k values. Applying our mind to this new, simpler problem, it becomes evident that k satisfies the inequality k is greater than or equal to 2 and less than or equal to n plus 1. K cannot equal 1, since in that case, x and y would each have to be natural numbers less than 1, of which there are none. Z can obviously equal the upper bound of n plus 1. Translating our findings to sigma notation, we write the following. The number of elements in T, which equals the sum from 2 to n plus 1 of k minus 1 squared, equals the sum from 1 to n of j squared. The quantity k minus 1 is replaced by j. When k equals 2, j equals 1, and when k equals n plus 1, j equals n. Finally, replacing j with k once again, as they are both dummy variables, gives us the number of elements in T equals the sum from 1 to n of k squared. This ends method 1. In method 2, we will establish conditions relating x and y which we did not have to do in method 1. Broadly speaking, there are three main categories: x less than y less than z, x equals y which are both less than z, or y less than x less than z. In the second category, we are only required to select two distinct elements from the set S, one to represent z and one to represent x and y together. There are n plus 1 choose 2 ways of doing this. For the first and third category, we have to select not 2 but 3 distinct elements for each of x, y and z. Each selection of this type will account for 2 elements in T, one for x less than y less than z and one for y less than x less than z. Hence the binomial coefficient n plus 1 choose 3 will have to be multiplied by 2. Summing everything, we have the number of elements in T equals n plus 1 choose 2 plus 2 into n plus 1 choose 3. This can now be verified with the well-known formula for the sum of the first n squares. That is, Sn, which equals 1 squared plus 2 squared all the way up to n squared, equals n into n plus 1 into 2n plus 1 all upon 6. N plus 1 choose 2 plus 2 into n plus 1 choose 3 can be rewritten as n into n plus 1 upon 2 plus 2 into n plus 1 into n minus 1 upon 3 factorial. Factoring out n into n plus 1 upon 6, we have inside the parentheses 3 plus 2 into n minus 1, which equals 2n plus 1. And the formula is verified. Though the binomial coefficient n plus 1 choose 3 remains undefined for n equals 1, the formula for the sum of the first n squares still works, since the algebraic definition we have made use of, namely n into n plus 1 into n minus 1 upon 3 factorial, simplifies in that case as n minus 1 equals 0. Thus we can simply leave out the term n plus 1 choose 3 and our answer stays the same. Now, an alternate proof for the sum of the first n squares runs as follows. We begin with the identity k squared equals k plus 1 choose 2 plus k choose 2. This is valid for all k greater than or equal to 2. Verification is a quick process. Expanding the binomial coefficients algebraically, we get that the RHS equals k into k plus 1 upon 2 plus k into k minus 1 upon 2. Pulling out a common factor of k upon 2, the expression that remains is k plus 1 plus k minus 1, which equals 2k. And obviously, k upon 2 into 2k equals k squared. Summing both sides from 2 to n, we have that the sum from 2 to n of k squared equals the sum from 2 to n of k plus 1 choose 2 plus k choose 2. The sum from 2 to n of k plus 1 choose 2 equals 3 choose 2 plus 4 choose 2 plus 5 choose 2 all the way up to n plus 1 choose 2. To the RHS, we will add 3 choose 3 and subtract 1. The effect this has is to collapse the RHS to n plus 2 choose 3 minus 1. To see this, we simply have to apply Pascal's identity, which states that n choose k plus n choose k minus 1 equals n plus 1 choose k. This is essentially a restatement of the fact that each element in Pascal's triangle, except for those on the edges, are the sum of the two elements adjacent to it and then in the row above it. The only conditions demanded by the identity are n greater than or equal to k and k greater than or equal to 1, owing to the fact that k minus 1 is greater than or equal to 0. To prove the identity, we observe that 1 upon k plus 1 upon n minus k plus 1 equals n plus 1 upon k into n minus k plus 1. The k cancels out with the negative k after creating common denominators. Then just multiply both sides by the quantity n factorial upon k minus 1 factorial into n minus k factorial. And take note of the fact that n plus 1 into n factorial equals n plus 1 factorial and n minus k plus 1 into n minus k factorial equals n plus 1 minus k factorial. After the dust settles, what we are left with is Pascal's identity. A second application of the same identity gives us the sum from 2 to n of k choose 2 equals 2 choose 2 plus 3 choose 2 all the way up to n choose 2, which equals n plus 1 choose 3. Putting the pieces together, we get the sum from 2 to n of k squared equals n plus 2 choose 3 minus 1 plus n plus 1 choose 3. Transferring the 1 to the other side, we obtain that the sum from 1 to n of k squared, which equals Sn, equals n plus 2 choose 3 plus n plus 1 choose 3. Verifying using the algebraic definition of the binomial coefficients, the equation n plus 2 choose 3 plus n plus 1 choose 3 can be rewritten as n into n plus 1 into n plus 2 upon 6 plus n into n plus 1 into n minus 1 upon 6. On factoring out n into n plus 1 upon 6, the linear factor in the parentheses is n plus 2 plus n minus 1, which equals 2n plus 1. We can justify the formula as being true in another faster way as well. This relies on us identifying that n plus 2 choose 3 equals n plus 1 choose 3 plus n plus 1 choose 2. When this is added to n plus 1 choose 3, we get the very first expression we saw for the sum of the first n squares in counting the number of elements of T in the problem at the beginning of the video. Namely, the number of elements in T equals n plus 1 choose 2 plus 2 into n plus 1 choose 3. With this out of the way, we are now ready to look at one last method for computing the sum of the first n squares that relies on a telescoping sum. We make use of an identity pertaining to the difference of two consecutive cubes as the seed that will generate our telescoping sum. In particular, k plus 1 cubed minus k cubed equals 3k squared plus 3k plus 1, which equals 3k squared plus k plus 1. Summing the left and right hand sides from 1 to n, we have the sum from 1 to n of k plus 1 cubed minus k cubed equals 3 into the sum from 1 to n of k squared plus k plus the sum from 1 to n of 1. Now to our good fortune, the left hand side telescopes. This is since one sum gives the sum of cubes from 2 to n plus 1, and the sum that runs parallel to it gives the sum of the cubes from 1 to n. The second sum is then subtracted from the first. Hence the left hand side condenses to n plus 1 cubed minus 1. The right hand side yields 3Sn plus 3 into n plus 1 upon 2 plus n, where Sn stands for the sum of the first n squares. Moving all terms but 3Sn to the other side, we get 3Sn equals n plus 1 cubed minus 1 minus 3 upon 2 n into n plus 1 minus n. Cancelling out the minus 1 with the 1 from the expansion of n plus 1 cubed further simplifies the equation to 3Sn equals n cubed plus 3n squared plus 3n minus 3 upon 2 into n plus 1 minus n. Hereafter, we can factor an n upon 2 from the RHS, giving 2n squared plus 6n plus 6 minus 3n minus 3 minus 2 in the parentheses. To see that it indeed is the case, one can simply multiply out the expression on the right hand side to re-obtain the equation from the previous line of working. The expression inside the parentheses then simplifies to 2n squared plus 3n plus 1, which factors neatly to give n plus 1 into 2n plus 1. Finally, bringing the 3 over to the other side, we see the same and by now very familiar expression for the sum of the first n squares. That is, Sn, which equals 1 squared plus 2 squared plus 3 squared all the way up to n squared, equals n into n plus 1 into 2n plus 1 upon 6. All this serves to reassure us of the fact that the three methods used here and elaborated in full are completely valid lines of reasoning and all lead to the same answer. An interesting fact that one notices over repeated problem solving is that this approach of using multiple lines of reasoning in solving the same problem works very often and fails only a few times. In other words, there exist a large number of problems in mathematical literature where one does not have to be confined to solving the given problem in only one way. Rather, there are an array of different options open to those solving the problem, and they can freely choose which one they wish to follow. This grants them the liberty to choose that explanation or solution which most closely matches their strengths and weaknesses. So if they ever find themselves uncomfortable with one method of solving a problem, they can trade it off for one that they are more comfortable with. And with that point being mentioned, this video, where we have given 3 different proofs for the formula that generates the sum of the first n squares, draws to a close. I hope you enjoyed every moment of it and learned some useful problem solving tools. Thank you for watching and see you next time.